This final clip will be on the limiting reactant problem. Students very often have trouble with limiting reactant problems. And because of that, chem teachers, high school chem teachers, and gen chem teachers have invented dozens of ways of doing the limiting reactant problems. And a few years ago, I started making a study about how well students did on Chem 2070 exams with different methods. And it became clear to me that there was one method where students did better at getting the right answer with cognitively complex limiting reactant problems. And therefore, I'm about to teach that method for you. Because remember, when you get a limiting reactant problem in the test, it may not be the ordinary variety of it. It may have some cognitive twists. And this is the method which has been proven by 2070 students to be the best, and therefore it's the one that I'm about to teach you. And I'm going to teach you the method, and I'm going to teach you the method for this problem right here. 2.31 grams of H2SO4. It's the same reaction we had before. And 1.34 grams of AlOH3 react in water. How many moles of H2SO4, AlOH3, and Al2SO43 are there after the reaction is 87.2% complete? And that's the problem I'm about to do. So we start by writing the balanced chemical reaction, which we know from last time is 3 H2SO4s, 3 sulfuric acids, plus 2 AlOH3s, aluminum hydroxide, going to aluminum sulfate, plus 6 waters, the balanced chemical reaction. And the method I'm going to teach you is based on the ICE table. And we're going to, what is the ICE table? The first line will be I for initial. C100, C100 for complete reaction, complete change. C, since we're going to do in this problem 87.2% complete, we'll do C 87.2. So 87.2% complete. Complete change. And finally E, which we can think right now is the end. But in 2080, E will stand for equilibrium. And this is called the ICE method because of the different rows. And the ICE method in 2070, the entries will be in moles. And in 2080, when you use the ICE table, the entry will be most often, but not always, in concentration. So we'll be doing ICE tables in moles, and you'll see another variant of it next semester if you go on to 2080. Okay, so that being true, we only can enter things in moles, and so the data of the problem is that we have 2.31 grams of H2SO4, and we need to turn it into moles, and so we divide by the molecular mass of H2SO4, which is 98.08 grams per mole, and we discover that this is and remember that I always go for more digits and intermediate steps. 0.02355 moles of H2SO4. The other number we had is 1.34 grams. 1.34 grams of AlOH3. And we divide that by its molecular weight, which is 78.00 grams per mole. And that's equal to 0.01718 moles of AlOH3. And so now we have numbers in the mole form. These are in the mole form. Here and here. And so I can introduce that right into the table. 0.02355 moles of H2SO4 and 0.01718 moles of AlOH3. And if you take moles of a compound and you divide it by the coefficient of the compound in the balanced chemical equation, put in chat what you think that is. The moles of a compound, oops, I do better move this up top. The moles of a compound divided by the coefficient of the compound in the balanced chemical equation. What do you think that's equal to? It's something we talked about last time with a little subscript. Put it in chat, please. That's right. That's the mole reaction. So we take 0.02355, we divide it by 3, and we get 0.00785 mole reactions. We take 0.01718 divided by 2, we get 0.0086 mole reactions. And the smaller mole reaction is the what? Put it in chat, please. The reactant with the smaller mole reactions is called the what? Put it in chat. Yeah, thank you. It is the limiting reactant. So in this case, the limiting reactant is H2SO4 because that's the smaller number. And that means the limiting reactant controls the show because in the complete reaction, the limiting reactant is the one that gets completely used up. So at a C100, put in chat how many moles of H2SO4 will get used up because it's the limiting reactant. Put it in chat, please. It gets all used up. That's because it's the limiting reactant. So it's minus 0.02355 moles. And the C87.2 will be 87.2% of that. It'll be minus 0.02, if you put in the calculator, 054 moles. Good. So we go down in the column for the limiting reactant because it's the one that gets all used up. And now comes the key. In the change line, in the C100 and C87.2 line, the ratio of the mole amounts is dictated by the reaction compound coefficients. For every 3 H2SO4s, 2 AlOH3s are used. And therefore, for what number here, CC100 is 0.02355, 2/3 of that amount of AlOH3 will be used. So this will be minus 0.01570 moles. And how many Al2s SO4 will be made? For every 3 H2SO4s used, 1 Al2 SO4 is made, and therefore the number of moles of Al2 SO4 will be 0.02355 divided by what? 0.02355 divided by what? Put it in chat, please. Yes, it will be 0.02355 divided by 3, because for every 3 you get one of those, and it'll be a plus sign because it's being made, 0.00785 moles. And here, 6 times the amount plus 0.0471 moles. And we started off with 0 of these guys. And C87.2 will be C87.2 will be exactly 87.2% of the C100 lines, so it's going to be minus 0.01369 moles. 87.2% of this is 0.00684 moles and 0.0411 moles, and the E line is the I line minus what the actual change was. And the actual change here was the 87.2 line. So we take the I line and, I'm not subtracting, but add. The I line plus the change is the E line. So we add these two numbers and we get 0.0030 moles of H2SO4. Take this number and this number and add them together. We get 0.0035 moles of AlOH3. 0.00684 moles of Al2SO43 and 0.0411 moles of H2O. And these 4 numbers are the answer to the problem.